Okay, cool. Hi, everyone, and welcome to the 10th IAP lecture. Today, we're going to be doing emotion, dialogue acts, personality, and lying. But first of all, this is our last week of IAP, so I was just going to give a brief kind of overview of what we've done so far. So think back to the first week, we looked at kind of audio, how you get audio into a computer, essentially. The second week, we then looked at kind of text representations, tokenization, word embeddings, and then the kind of transformers, the key parts of NLP. And we did kind of more language modeling. Last week, we then looked at the kind of end-to-end system of how you get speech into a computer, then, I don't know, do dialogue, process it, dialogue systems, and then how you then put it back out into speech with text-to-speech. So having looked at all of those kind of parts, this week we're going to be doing slightly more sporadic topics. And today we're going to be looking more at kind of speech content. So if you think about a speech signal, you have in it the text, you have all of these audio features, the frequencies, the formants, the harmonics. But there's a lot more information that humans derive from just a segment of speech than what is kind of obvious just from seeing the representations. For example, you can tell emotion, personality. There's been some research recently into detecting mental health, and over COVID, there was some research into like, can you detect if someone has COVID just from how they sound over the phone? So today we're going to be digging a bit more into this kind of speech content. And we're going to be looking at textual features, but mostly kind of audio features. And then the third kind of aspect of emotion and conversations, dialogue acts would be visual features. Since we're mostly looking at speech signals, I'm only going to touch on this briefly, but these are kind of all things that a human will automatically take into account when you're making a decision over how someone's feeling, what they're saying. And these are the kind of things we want to be able to, the information we want to be able to extract. So without further ado, first of all, what is emotion? Like, am I happy? So you might have seen a lot of, with NLP, semantic analysis or semantic content. The kind of stereotypical example is like Amazon reviews. Is someone happy? Or is it a positive review or negative review? So I first of all want to just draw a distinction between like semantic meaning, like reviews, and more of an emotional state, like a human emotional state, kind of what someone's saying, what like their versus what they're feeling, and that's more kind of non-linguistic. So, okay, we're gonna get started with the valence arousal model, which is like the very stereotypical emotion model. It's the circumplex model. It was originally kind of proposed by this guy Russell in 1980, and it basically hypothesizes that any emotion can be charted on two axes: valence, negative to positive, and arousal, like low energy, high energy. So sadness would be like low energy, negative. Excitement would be like high energy, positive. And this is kind of a nice framework when we're looking at emotion in the brain. So what is an emotion? It is a result of neurotransmitters in the brain. Specifically, these three tend to be kind of thought of as the emotional kind of neuromodulators. So dopamine, serotonin, norepinephrine, am I saying that right? It's kind of an adrenaline-based, similar to adrenaline. Same thing, there we go. And in the brain, this is situated in two different areas. You have it in your amygdala, which is kind of more deep-seated. I have a stick. Deep-seated, and that's kind of your like very more kind of primal responses. So that's flight, fright, freeze. And then in the orbifrontal cortex, that tends to be more of the valence side. So like slower, but negative, positive. And one fun thing about this is that there is also like spatial situations. So in the orbifrontal cortex, like negative emotions tend to be seated towards the left-hand side and positive towards the right. So if you're looking at like brainwaves, there's some kind of research into identifying emotion based on location for valence and frequency of the brainwave for your kind of arousal level. So relaxed would be kind of alpha waves, I believe it is. And then higher frequencies is when you're like getting more excited. So one kind of way of thinking about this is that the arousal axis is that amygdala, and the valence kind of tends to be more in the orbifrontal. Very, very, very overgeneralized. This is very much an ongoing area, obviously. So emotion has kind of developed as biological advantages. It's an evolutionary trait. And one of the main things for this is like, you see teeth, you run. Fear was like one of the main evolutionary advantages of emotions. And there's a thing where it actually, for your optical system, it bypasses a lot of kind of conscious processing. And so if you see like teeth, or if you have shadows kind of going over you, it's going to trigger a release of those kind of fear hormones. And even if you don't really know why, so apparently, like if you have someone in a room and you just have shadows going over them constantly, they're just going to keep getting these fear hormones, and eventually they're just going to be really freaked out, even if they don't really understand why. And that's kind of an interesting thing to think about when we're trying to emulate emotion, in that we also do this with like speech. Like if someone screams, you don't react to the words in the scream. You react to the fact that they're shrieking really loudly. Similarly, laughter, you actually, the sounds don't go through like linguistics, the linguistic processing side. So just an interesting thing to think about moving forwards. And so the other kind of advantage of emotion is societal. Being able to understand other people's emotions and how you're affecting them and what they're kind of feeling in a situation is kind of the basis for human like interactions. And like without human interactions, we don't have like society, I guess. Cool. So why do we care? Like we're a speech language company and we're making a voice bot. So humans respond to emotional tone like often like times before the actual language and the text. If you say something sounds robotic, you tend to mean it sounds monotone. And so like if you're designing a bot, you want it to be able to not just detect the emotion that's being of the person and respond to it. You want it to be able to change action, and you want it to be able to react in a way that we as humans expect it to, given the situation. So moving from emotion, we are going to turn this very abstract conceptual theory into a vector, because that's all we know how to do. There are three views of this kind of emotion vector. You can have it as dimensional, so this is continuous space. So this is an example of this would be the valence arousal model. Categorical, so like distinct independent categories. And the third, which we're not really going to get into, is kind of cognitive appraisal theory. And it's this sense that it's emotion is a function of your kind of personal effects, personal relevance. So this might be novelty, it might be goals, it might be that kind of thing. So we're going to focus on these two. So first of all, I'm actually going to start with categorical. So in 1962, this guy called Tompkins said that emotions, there's a limited number. He proposed that there were a limited number that are genetically pre-programmed into the brain. They are triggered by changes in stimulation. And he proposed these 8 emotion categories and basically said, this is it. These are your emotions. Have fun. Bye. There's been developments on these, like a couple other people proposed different lists. They all share similar things in terms of they all have fear anger, disgust, these kind of pretty behavioral aspects. And eventually, Plutchik came up with this theory that emotions are psychoevolutionary. So your basis categorical emotions are based on what was evolutionarily advantageous. And he came up with these 8. And the kind of nice thing about Plutchik's theory is he put it onto the kind of wheel of emotion, and he put them into pairs. So the idea that opposite this wheel, these are pairs of emotions, so grief and ecstasy are opposite, terror and, is that rage? Are opposite. And that you can, these are the basis, and you can achieve any other emotion by mixing these. So disapproval here is a mixture of grief and amazement in some form. So it was like paint. Basically, your primary colors are your primary emotions, these 8. And this is a fun sticker I found on Zazzle. You can just take this to the extremes. But this is kind of, again, the similar idea of the color wheel. Cool. So that's a brief overview of categoricals. Looking dimensional. So the valence arousal model, you can add, people tend to add a third axis, sometimes one for body language I've seen, but focusing more on speech. A traditional one to add is dominance. So valence is like negative, positive, arousal, energy, and then dominance is how kind of forward that is. An interesting new one, I think this was 2012, is actually having the neuromodulators be the dimensions. So those kind of 3 main neuromodulators, the amount of those that are present in your brain when you're experiencing that emotion gives you the vector of like where you are. It kind of brings up the question though, how many dimensions do you need for emotion? Traditionally, these all kind of model it with 3 parameters, but machine learning techniques allow us to scale this up to embeddings with 256, 512. I'm going in passive 2 because that's all I know how to do. We can take this to the extreme. So this is an ongoing area of research, is how many parameters you need to kind of embed, encode an emotion embedding. Cool. So that's kind of a brief overview of how we might represent emotion. Any questions, concerns, emotions? No? Yes.
The categorical people at all think that have infinite numbers on each of those categories in this area?
So the question was, do the categories have like varying amounts of each? Is that correct? Or is it just like discrete? So the original theory of categorical is that it's like Tompkins' theory was that you are in one or the other. You can be, Plutchik was basically saying you can be in more than one. And that's the kind of mixing of it, right? To get the different type, but everything is a mixture of those 8 basics. Yeah. Anything else? Cool. So moving quickly on to the kind of other aspect of this topic, of this lecture, dialogue acts. So emotion is one thing we can get from what you're saying. Dialogue acts is another kind of trait we can take away from an utterance. And the kind of idea of a dialogue act was first proposed by this guy Wittgenstein in 1958, and it was this. There were a few theories at the time as to what constitutes the meaning of a sentence. One was that the meaning was positive logicalism, is that the meaning of a sentence is just the absolute truth of that sentence. Another one was that it's the action that results from the sentence. So if I say go over there and the person either moves or doesn't move, but it's the actual action that constitutes the meaning of the sentence. Wittgenstein proposed that it's the function of a sentence within, the function of an utterance in the sentence that gives it its meaning. So kind of examples of this might be if I say the word hello, and I say, oh, I'm not going to say hello. If I say, how are you? And we were always told when we first got to America that as international students that how are you doesn't mean how are you. People don't expect a response. So in that sense, the function of the sentence, how are you, has the functional meaning of hello. It is functionally a greeting within the sentence. And so the dialogue act of it is a greeting, even though you might think how are you is a question. Conversely, if you actually say how are you with the intention of getting a response and you wait for an uncomfortably long period of time for someone to respond, then it takes the functional form of a question, and then its dialogue act within the sentence is as a question. So this is kind of just an illustration of how the meaning is related to how you are functionally using that within your sentence. And this is like really important for conversation signaling. It's how we roadmap conversations. It's how we know how to respond. There are some kind of expected QA response things, and there'll be more on conversation design in tomorrow's lecture from Cooper, so turn up to that. But it's important when we're trying to design a bot, because a bot needs to understand when it, what function a person is using a sentence in so that they can respond accordingly. So having kind of overviewed emotion and dialogue acts, how do we actually identify the emotion within like an utterance or the dialogue act within an utterance? One of the kind of key things that humans key off of is prosodic features. So prosody is kind of your rhythm, your intonation. So I have a tendency when I'm presenting to kind of go up at the end of my sentences in a vaguely annoying manner. So this would be a prosody change that happens in my voice when I'm presenting. Kind of some examples of prosody as far as emotion goes. Pitch, sometimes you might think is equitable with intensity. If you're sad, you might downturn your sentences. And this gives a sense that you're just really kind of low energy and sad. Whereas if I upturn, it feels more energetic, which is probably why drama teachers used to tell me to speak like an American, because Americans tend to upturn their voice at the end. I don't think that's true, actually, having been here now, but that was what I was told growing up. The other sense is this, if I were to say anger, and I say cold anger or hot anger, everyone kind of has a sense of what that means, even though it's technically the same emotion. But hot anger tends to be like higher frequencies and more intense. Cold anger, lower frequencies, sarcasm, humor. The point that I'm really getting at is that humans are very good at this, and we don't often know why. You identify an emotion in speech, you might write some hard rules for why, like downturns, upturns, but at the, like, there's a lot of nuance in the prosody that affects how you kind of interpret a sentence. Dialogue acts. Again, this is the question, this is the question. You kind of get the idea. One key fun one, I think, with dialogue acts, though, is like sarcasm. So if I say a sentence and I mean it literally or I mean it sarcastically, I might change the intonation, and that changes its function within the sentence as it becomes from a statement to a joke. And this is kind of an example of how, yeah, prosody changes the dialogue act. Swear words. So again, this is another kind of example of where the actual words are somewhat irrelevant. It's a highly effective language use. It depends on how you kind of relate those words. But there was a study where children were told in class that they weren't allowed to say swear words. They had to replace them with the words swear word. So, like, rather than ever saying a swear word. And these kids went home, and after a couple of months, they're sat around the dinner table, and one of the kids turns to the other and goes, "Oh my God, you're such a swear word." And the other kid gasps and goes, "Oh, you can't say that." The parents sitting there like, what's going on? Like, the teacher in the end had to ban the words swear words, because the kids were using it with the same functionality as an actual swear word. So it still had the same kind of function within the sentence. I thought that was funny. Final thing on prosody, lying, deception. So we tend to modulate our voice in ways that we don't really fully intend when we're lying. Part of that is because you start to pay more attention. I've been talking a lot about how a lot of this for humans is intuitive, subconscious. When you're lying, you tend to suddenly pay more attention to what you're saying and more attention to how you're saying it, and it sounds off. So there's apparently females tend to increase their uptalk when they're lying, whereas males tend to go towards more monotonicity. There's probably some things to dig into there, but truthful versus untruthful language, like using specific words that signal truthfulness. Hyperbole, performative language tends to skew towards lying, and the use of kind of over-explaining. I'll get back to why I'm talking about this in a bit, but final thing, I know I said the last one was the final thing, I lied. Different cultures have different prosodic trends. So imagine you're like brushing your teeth and you're trying to communicate with someone, but you can't use words. We tend to just kind of mumble along with like prosody, and you can kind of generally get a sense of what people mean. If you were talking to someone who spoke a language with a different prosodic trend, that actually wouldn't be true. So again, this is just more sense that a lot of our meaning comes from the prosody, not just the language. Also, yeah, you have different emotional associations with different languages sometimes if you're multilingual. So one demo, I'd like everyone to close their eyes, and I'm going to say the same sentence. Once I'm going to say it without smiling, and another time I'm going to say it with smiling, and I want you to guess which one is which. And I'm going to try and keep everything else the same. I should have prepared a sentence for this. Okay. The sheep was singing in the field. The sheep was singing in the field. Which one was I smiling in? We have complete consensus. It turns out that when you smile, you like just the way your muscles move in your face and the way your mouth stretches, it changes the frequency, it raises the frequency a bit, and it changes some of the formants of what you're saying. And again, humans over the course of many years have learned to associate that very specific change with the act of smiling. So you can picture someone smiling when you hear that. This is, again, something that we would want to train a model to be able to pick up on. But humans are very good at it. Cool. So this basically comes down to we want the ability to process prosodic cues for interactional coordination, which I thought was a nice soundbite. And this brings me to doing this. What am I doing for timing? Good. Oops. Okay. Cool. Speech emotion recognition, SER. Before I get into this, any questions? That was kind of a very rambly discussion of different prosodic things. Cool. So having kind of looked a bit at what features in speech that can tell us things, we now want to like train something to actually then like recognize that. So the way kind of a very often used model is wave-to-vec. And the idea here is that we want to take a speech waveform, and we want to learn some feature representation of that waveform such that we can then kind of extract information from that. So wave-to-vec is a model that takes your waveform, it puts it through CNNs, and you learn some latent kind of representation. It then does kind of BERT-style masking, puts through a transformer, and you get out these context representations. And this would be our feature embeddings. So this is a way of getting a lower dimensional, since the speech waveform is very high dimensional signal, context representations of an audio form. The way it does, like its loss function, initially it's a self-supervised training. So its loss function is based on contrastive loss and diversity loss. So the contrastive loss is you're trying to maximize the mutual information between the, like it quantizes these representations. This is kind of like splitting the signal up. And you're trying to maximize the mutual information between the correct one of these and your context representations, and minimize the like negative examples. So if you have the wrong one, basically the wrong cue, and this gives you this kind of takes your audio waveform, and we get some feature embeddings from it. There are other ways, but this is kind of a very standard model for it. So this is just an example of kind of what we're trying to do with contrastive loss. We're trying to essentially make sure that two examples of the same thing lie next to each other in vector space, and the kind of examples of opposite things lie as far away from each other as possible. So this model used, the original wave to vector uses a transformer as its encoder there, but there's been some variations where you use a conformer. I know Won Kim talked a bit about conformers when he did his ASR lecture last week. And this is the same process. You've got the masking, you take the quantization, you do contrastive loss with the output from the conformer blocks. And this is the self-supervised step. You then fine tune on top of this, and this is kind of, and then towards the actual use case you want. And get back to that later. But if you want to train a predictor to predict an emotional category, you want to take your speech signal, you want to transform it into its context representations, and then you want to train a predictor to predict the category from those from that embedding. So when you need to decide on your categories, we already spoke a bit about like the different theories of categories, but some considerations you would need to make, like the lexicon tends to have more negative words than positive. There's more of a need. If you're happy, you don't need to talk about it as much. If you're unhappy, apparently there's finer grained granularity to that. You probably want to choose emotions with kind of distinct features, or emotions categories that are kind of as far apart from each other as possible. So you can look at existing theories and also specific use cases, like what do you specifically want to be able to identify between. So once you've chosen those, you can take your embedding space, and so this was our wave to vec 2. This is the fine tuning step where you would like tune it on its supervised training. So you would train it on data pairs where you have the audio and the emotion out. And then you end up with a predictor that can take in these feature representations, and output a prediction as to what category of emotion is being felt. So there's been some kind of variations on this. This is this is an example of how to do this. You can use teacher-student training, so you can train a model to actually categorize just this emotion exists or it doesn't, and you can train one for each of your categories, and then use those to train a model that can output like a probability of each. You can incorporate visuals. So there's been some research in like videos and actually having not just the audio, but a visual, like another kind of feature embedding, but of visual features. And there's also been some with like textual. So having a BERT-style language model that you also have the output from that feed into your predictor. And that kind of brings me to the data side. Since the fine-tuning step, you need labeled emotional data. And there's really, like, emotion data sets out there tend to be pretty small. So how do you kind of deal with this as an issue? Also, emotion categories are non-exhaustive, unless you subscribe to Tomkin. But if you have an emotion that is not within your data set, how do you deal with that? And there's been some advancements recently using zero-shot learning for this. So there was this kind of cool paper from 2019 that was using this kind of effective structural embedding. So they actually had a mid-level representation using adjective-noun pairs. So they were using their model to learn the features that went into those adjective-noun pairs, and then using that to, if they had this was for images as well, but same thing. If you had an unknown category, you could then map it to its nearest unseen category if it fits that mid-level representation adjective-noun pair. So I would recommend reading it. It's kind of fun. And this is using, I believe, Ekman's 8, and then these are the kind of ones that are unseen. So this is if you went for those as your initial 8, but then these are unseen categories. Cool. Any questions, thoughts, concerns? Yes. So this one used audio and images, I believe, together, or it was just images. But you could do it for audio in theory. Yes.
What is like an example use of the model?
So an example is that, like, you've had the question. I realize I didn't. The question was an example use of the model. If you trained it with these, just to recognize these 8, but then you have one that has like something else that lies outside of those 8, it would be able to cluster them still based on that kind of mid-level representation of emotions that is still similar to each other. Cool. So let's say that you can recognize emotion. This brings me on to kind of the next thing we would want to do with a bot, which is emotion tracking. How does emotion change over time? How do we change actions based on the emotion that we've either detected or that we decide that we want to output? So one idea of this is that how humans change emotions is like varies hugely, but we don't tend to just like switch from one to the other at like a split second. I mean, maybe you do, but there tends to be some kind of sloping gradient. So you can kind of think of this as if you're changing emotional state, you either want to regularize it in some way so you're not like taking huge leaps if you're going for a numerical approach, or if you're in categorical kind of world and you exist in an emotion state, there's probably some kind of order of probability with which you would jump. So you might jump like happy to neutral to sad rather than just like happy to incandescent rage. And this lends itself to kind of an idea of like Markov chains. So just exploring this as an idea, like if you were to maintain state categorically, let's say we only have 3 states. We've now reduced our emotions to 3 possible emotions: happy, neutral, and annoyed. And let's say someone stole your sandwich. So this might be an idea of kind of how you might change state if someone steals your sandwich. If you're neutral, you might kind of stay in neutral and go to like, it tends towards annoyance at every stage because No one really likes their sandwich being stolen, unless you're in the 0.02 who go from annoyed to happy when someone steals your sandwich. And then we can kind of think of the personality effect as being like different probabilities of this. So this might be a very kind of average one, but let's say you're an easily irritated person. You might have even more emphasis on the annoyance. So this is kind of one idea that human personality affects how you're going to take an input and how you're going to transition emotion. And so if we're thinking about kind of how we want to model emotion, we probably also want to take this into account. Other things that might like affect, I don't know, if it was a peanut butter jelly sandwich, you might be more annoyed. So this also kind of comes to one other traditional theory, which is the opponent process theory. I know I just said that you don't tend to like switch states, but there's also a theory that your initial reaction to an emotional event is going to be followed up by like the opposite emotional state. So think back to Plotchik's color wheel. If you're having one intense emotion and then it ends, you're gonna tend to flip into the opposite emotion. So like pleasure, pain, depression, elation, fear, relief. Just another thing that you might want to think about if you're doing state emotion tracking. So, and this is, I'm not going to get too far into this, but does this kind of remind you of anything? Make you think of a method that you might immediately want to apply? No? That's cool. It kind of made me think of reinforcement learning. Reward-based mechanism, simple reward, you want positive emotion, and you can learn an action policy based on your current state, based on observations, and there's some research into this for kind of creating reinforcement learning based bots, but like I said, I'm not going to get too far into it, just so that kind of brings us around the kind of like a bot should be able to process prosodic cues for interactional coordination. And the final thing I'm going to talk about is that a bot should be able to process and reproduce prosodic cues for interactional coordination. And this is because you want feedback that you've been heard. You want feedback that you're like, it's all very well a bot can like be like, oh, this person is sad, but if they still then turn around and go, that's a shame, you're going to feel annoyed. So you want it to be able to react verbally and reproduce those prosodic cues. This is a very high-level diagram, honestly, but it kind of harkens back to what Lockman was talking about in the TTS lecture, with the idea that you can actually add embeddings to a text-to-speech with the idea of changing how the output sounds. So before we were looking at it with different speakers and kind of different speaker embeddings. There is research out there to suggest that if you put emotional embeddings into the text-to-speech, you can also do the same, use the same process or similar processes to produce smell spectrograms with the prosodic kind of emotional cues as in the same kind of manner. So that's kind of all I really had on that. Do we have questions? Otherwise, I'm going to jump into a demo.
Hi, Phoebe. I don't have a question, but I have a bit more of a curiosity.
Yeah.
So you mentioned about reinforcement learning and emotions, and I looked into emotional valence as part of my research, and you actually hit the nail on the head because, oops, that's my cat, because there is a lot of extensive research about emotions by this neuroscientist called Edmund Rolls, and he says that, you know, emotional valence is depends on the delivery, termination, or omission of rewarding and punishing stimuli. And at the same time, there are other theories of emotion which rely on, I don't know if you heard about the free energy principle, and essentially they describe emotional valence as the, how much prediction error there is. So if there is an improvement in learning rate, we have more positive emotions, and if not, if there is a decrease in a worsening in learning rate, then we have more negative emotions. And I thought it would be cool to see if with this research that you guys are doing with this work, you can tell whether someone expects something or not just based on the emotions they have. Yeah, it's more of a general curiosity, but I find this really cool.
That's really cool. Like, are you basically saying that like so you're saying that the loss is based on like your expectation versus the reality as opposed to like absolute state, and it's like
Exactly,
more
yeah.
that difference that is the valence?
Yeah, it's one of the theories of cognition. It's from this British neuroscientist, Carl Princeton. And essentially he states that, the way that we process the environment and we interact with it is to minimize this surprise. But surprise is in terms like information theoretical terms. I think you spoke about this in week 2. Like it's literally the logarithm base 2 of the probability of the event. And he says that everything we're trying to do and the way that we interact with the environment is to minimize this surprise. And so they also see emotions in this way. So when we minimize the prediction error, then we have more positive emotions.
That's cool. So by the idea being that like if you're it's essentially you're trying to trend towards as neutral as possible. You don't want like you don't want to be like differences in.
Yeah.
That's
yes.
cool.
Yeah.
That would be in it. So like going back to what was it? Instead of the reward being happy human is good, we're rewarding it based on just like absolute chill level. We want to be as chill
more or less how
possible.
correct your predictions are. Yeah,
Nice.
I would say how correct your predictions are.
That's really cool. Thanks.
No worries.
I don't have much to add to that beyond, but
yeah, no, I just thought it was really cool to think of this in terms of what we're doing here.
Yeah. Nice. Any other? Cool. I'm gonna jump into a quick demo then. So this is just a quick demo on emotion categorization, and how you can kind of output these. So take your emotional outputs and use a softmax to turn them into like a probability of each being in existence. So for example, if I just record myself saying something like, oh, I'm really sorry about that. It's going to be very awkward if it tells me that I'm mad. Also, my setup is a little convoluted, so it takes a little while. But whilst we're waiting for that to output. Any other questions? Yes.
Are the emotion models with language models built into them drastically?
So like there's been some improvements with like having some text, but honestly the biggest like improvements came with visual. Yay, most likely emotion apologetic. And this is kind of you can see apparently relieved was pretty high as well. Visual information actually has shown a lot of the best results. We just have, yeah. To repeat that, like the question was how much kind of adding language models, so you have the textual information as well, would improve. And a couple of years ago, and there was this, it was kind of seemed to be roughly equal contribution, but I believe recently there's been improved, like it does improve it from what I've seen. That's very hand wavy. Yeah, I can try another emotion. Does anyone have an emotion they want me to? What if I say a really nonsensical sentence in a really angry tone? A hot anger, but a really boring sentence, like passing these positional arguments will result in an error. I really hate. I'm glad we don't have to actually listen to that. Hey, that was kind of obvious though. Let's see if it does something if I say something angry, but in a really calm tone of voice, like, or really happy. I really don't like this. I don't know what that's going to come out as, to be fair. Maybe that's worried.
Is this based on one of the categorization things you mentioned earlier in the slides?
Yeah, so this is based off, it's a categorical prediction based off conformer outputs or conformer like representations.
Do you happen to know how much label data was used to fine tune it?
No. In terms of hours, or just
There are a number of videos.
number of.
Okay, yeah.
Cool. Apparently that was surprised. Can I do sad? Does someone want to show me a picture of, like, I don't know. How do I do sad? I heard that they're going to take away Nutella. I have no idea if that's. Also, it's kind of like I've done a really dumb like extract top, like just literally the one with the highest probability, but because of how it was trained, sometimes like it's more of a presence of each. So even if one appears more likely, it doesn't necessarily mean it's like the top emotion, if that makes sense. It's thinking about it. Hey, it heard the word no Nutella and it was like, okay. Cool. Well, that's kind of all I've got for today. Oh, yeah, no, I have exercises. You're right. This is why we have slides. So these are just kind of exercises for next time. Record yourself saying the same phrase, different intonations. See if you can identify what you particularly as a person are like using when you say a sentence to indicate things. Take away the words, say the same sentence, but just with the intonations. Does it sound like it has the same meaning? And then like get a voice bot to say the same sentences and work out what they're using as intonation and what different intonation that. I'm pretty sure there's a way to like tell Alexa to repeat after me. There's not, there should be. And answers from last time. So how would you parse date times in frame-based systems? Cascades of regular expressions to implement rule-based approaches. And you can read more in Jurafsky chapter 22. Read this. That is the answer. Cool. Thanks for joining. Happy to hang out if people have any more thoughts. Otherwise. I don't know how to finish the recording on this, actually, since I did not start it. I'll leave that up there.